All right. Well, we're a little over on time for today, so I do want to go ahead and get started. Before I jump into the presentation, I want to thank NCGIS for the opportunity to present here today and all of you for attending. This presentation is going to be more technical in nature. It's going to focus on acquisition and production for airborne Lidar, specifically high density collected from unmanned aerial systems. Very briefly, I'll talk about McKim & Creed for those who aren't familiar with us. We are an employee-owned, multidisciplinary engineering consulting firm, 46 years in business, 26 different offices throughout the U.S., and over 900 employees at this point in time. From a services perspective, we offer a broad range of services. From a geomatics perspective, we focus on quality-based professional services for traditional boots-on-the-ground surveying, acquisition and processing for aerial, mobile, and terrestrial LiDAR and imagery, GIS services, hydrographic surveying, as well as subsurface utility engineering levels A through D. From a geographic footprint perspective, at least for aerial mapping, we do work all throughout the country. There's really not a state that we won't collect LiDAR imagery in for some reason. And then from a survey perspective, we're licensed in 18 different states right now to support projects. I'll very briefly introduce myself. So for those who don't know me, my name is Ravi Saneja. I'm a geospatial project manager with McKim & Creed. My background is in airborne LiDAR, specifically working with UAS LiDAR systems. I've done a lot of projects, everything from topographic mapping, corridor-based projects, so transmission distribution, network mapping, vegetation encroachment studies, and then roadway corridor projects for transportation design build. Beyond that, I've also got a lot of experience working with editing bare earth and building LiDAR for USGS countywide mapping projects, as well as drafting metadata for those projects. So some common misconceptions when it comes to the use of UAS, specifically focused on supporting aerial mapping and surveying. I'm not going to go through all these just for the sake of time, but the main one is that it's going to replace the need for a surveyor or boots on the ground. In my experience, I've not found that to be the case. It's generally always a licensed land surveyor working with LiDAR and imagery experts to make sure the project is successful, that we're delivering data that's of a high quality and meets the accuracy requirements for that project. The main takeaway from this slide is the principles and science behind LiDAR, the acquisition and processing of it, really are not changing. All we're doing is going from a manned aircraft down to a drone at this point. And so for those who are maybe not familiar with what LiDAR is, it stands for light detection and ranging. It can be airborne, mobile, terrestrial. It is an active sensor technology. What that means is the sensor is generating its own source of energy in the form of a laser that's pulsing and firing into a mirror that's either rotating 360 degrees or just oscillating back and forth inside the laser head. It is random sampling as well. So when I say random sampling, what I mean is if you've got a 1 meter by 1 meter panel target on the ground, we're going to be reasonably confident, depending on how we flight plan that, the sensor settings that we're running, that we can get a target off that panel or return off that panel. We just can't state with certainty where on the panel we're going to get that return from. And then lastly, the main advantage to LiDAR is, with most systems nowadays, is multiple returns per a single outgoing pulse. So when you have that laser pulse that leaves the scanner, the first return may come from the top of the tree. If there's enough energy left in that beam, it'll continue on. It might hit a branch, the trunk, and then the ground. So you're getting those 4 discrete returns from one single outgoing pulse. The main advantages to LiDAR, because it is an active sensor technology, it's agnostic as to when you can collect it. You can collect it day or night. Obviously, if there's an imagery component to your project, then that would restrict you to daylight or lighting conditions that are going to suit the imagery. The ability to penetrate down through vegetation, that's not foolproof, and we'll talk about that more in a second here. And then really with most of these UAS systems is the ability to get very high density data with a nice fidelity of different features that you might be interested in mapping. And then defining high density LiDAR, the presentation's titled High Density LiDAR. So most topographic mapping products can be supported with LiDAR that's collected at or between 8 to 20 points per square meter. That's somewhat subjective when you define high density LiDAR. I would say it's generally greater than 30 plus points per square meter is going to be high density. That increase in point density does give you an increase in surface definition, but there are diminishing returns to that, and we'll talk about that towards the bottom of this slide. Many of today's UAS LiDAR sensors are capable of getting 60 plus points per square meter in a single pass, and we're not talking about line-to-line overlap or anything like that. We're talking about one single pass, you're getting that high density. However, when you actually go in and start classifying for ground, even though you might have collected 60 plus points per square meter, you're really going to be only getting 16 to 18 points per square meter that are going to end up in that ground class. And that's what I meant by diminishing returns, in that, you know, we're going out and designing a project and hammering it with 400 points per square meter for a topographic mapping is, we're not really doing ourselves any benefit. We're just creating more data that we've got to process now. And then the other useful thing for UAS LiDAR sensors, like I said, that high density gives you a better definition and fidelity of features. A lot of the projects I've worked on in my career have been transmission as-builts or veg encroachment studies, so using UAS LiDAR for that has been a huge benefit. And then very briefly, what is photogrammetry? Quite simply, it's overlapping images that are used to create maps. It is a passive sensor technology, so it's relying on the external lighting conditions to be able to collect the imagery. Because of that, you need to consider cloud cover and sun angles when you're collecting. It's generally better suited for a bare earth site with minimal to no vegetation on it. With all that said, it's not by any means an obsolete technology. Most of our projects, we're using LiDAR and imagery combined to be able to create those final deliverables for the client. And then I want to very briefly touch on LiDAR versus dense image matching. For those who aren't familiar with it, dense image matching is a photogrammetrically derived point cloud. It's done typically using an off-the-shelf software, something like a Pix4D or an Agisoft Metashape. This is actually a fixed-wing manned collect up in Wisconsin, where we did a dual simultaneous collect for LiDAR and imagery at the same time. What you're seeing on the right is the imagery that was used to create the point cloud. So you can see it's a dense image matching point cloud, but even though it's collected in leaf-off conditions, you can see at the undersides of the canopy, you still have voids on the ground, even around the buildings and around some of those curbing features. But when you look at the image on the left, which is the actual LiDAR viewed by intensity, those voids are not present anymore, and that's because of that multiple returns from a single outgoing pulse that we're able to get down past those features into the ground. The best way that I could explain a photogrammetric approach to a project is if you're trying to use it to create a point cloud, it's basically a static shot. What you're going to see is all you're going to get. If there's anything that's obscuring the ground, you will not be able to see below it in that instance. The main question that we always get is, which one should you use for your project? The answer to this is it depends. There's a couple different things that we need to understand. The first is going to be site conditions. We'll talk about that in a moment. Features of interest, if we're just doing topographic mapping, that's going to be flight planned one way. If we're also picking up transmission distribution poles, that's going to be a whole other set of flight planning that has to be done for that project to pick up that feature. The deliverables that the client's looking for, the project specifications and the required accuracies. When I say required accuracy, I'm talking about the final product and the control that's used to either calibrate the LiDAR or AT the imagery and processing. We try to focus on taking a solutions-based approach, so we're working from the deliverables backwards to figure out what's the best approach for that project. And then, like I said earlier, conventional survey methods are almost always going to be used to supplement the LiDAR and imagery products for those features that we're not able to collect from the air. And this is just a quick overview of the aerial LiDAR workflow. For the sake of time, I'm not going to go through the whole slide, but basically you're designing flight plans, setting control, acquiring the LiDAR, calibrating it, classifying it, and then creating your final products and running QC throughout that. So from a project planning perspective, we talked about site conditions being one of those things. Obscured areas is something that we're always looking at, especially when we're collecting in leaf-on conditions. We try to collect as much as we can in leaf-off, but there's certain project timelines and applications, for example, a veg encroachment study, that we're not going to be able to do that. So the rule of thumb that we've found is if you're standing in a forest and you can look up and see light coming down through the canopy to the ground, you're going to have a fairly good chance of getting ground returns. Again, that's not foolproof. And when I say that, I mean the LiDAR scanner can only see where light can travel. So if that target is blocked for some reason, you're still not going to get returns on the ground in that area. And we very commonly for our projects, we'll drop into Street View if there's, I know you were talking about that earlier, if there's Street View imagery available, fantastic. We'll drop in and start looking around and try to see, is this a project we feel like we can fly with our sensor, or do we need to use a manned aircraft that's got a higher powered sensor? And then, so this image on the top left is the same image on the top left from the previous slide. That's a site in Raleigh, North Carolina that's near our headquarters that during leaf-on conditions, it is completely covered in kudzu. There is no seeing down through the ground through that. So for a site like that, we'd really want to wait till we have leaf-off conditions to actually go out and collect it. What that's going to give us is better representation of the terrain and fewer void or fully obscured areas that would require a conventional survey crew to come out and pick up those features. And so that's exactly what I did last week before I came here. We flew it really quickly, ground classified it. What you're seeing on the bottom is the ground classified LiDAR point cloud. On the top right is the shaded surface generated from that ground classified LiDAR. And you can see with the kudzu and the low-lying brush dormant, we're able to get down to the ground and get a lot more information back from that. So another aspect of project planning is, should we use manned or unmanned for the approach? So this is a 1,200-acre solar site that we were proposing on, and this is a standard practice for us. We look at any project both ways. We're looking at, from a project planning perspective, how many flight lines is it going to take us to collect a LiDAR? How many images are we going to have to process? How much control are we going to have to use for that project? And then will that project support the project specifications, or will that acquisition method support the project specifications and required accuracies for that project? And then lastly, and I think the most critical one, which of these is going to be the most efficient and cost effective for the client? Ultimately, that's what we're after. Just because we have a UAS LiDAR system does not mean we're going to try to shoehorn it into every single project we can if it's not the right tool for that job. I say all that to say I'm not telling you guys that one of these is necessarily better than the other and that you shouldn't go out and fly 1,000+ acres. If you want to, by all means do it. I did it once. I will probably never do it again. When we get to these 1,000+ acre sites, we usually will go to manned aircraft at that point. And then another aspect of project planning is acquisition design. The individual responsible for flight planning really needs to be familiar with the project specifications and the contractual requirements for that project. So they need to understand the point density that's required for the project, the required accuracy for that project, and the intended use of that data. There's a lot of commercially available off-the-shelf software you can use to flight plan, but some of those different parameters that we'll look at is % overlap that we need from line to line, scanner settings, so the pulse repetition rate, the scan line rate of the LiDAR sensor itself, what the scan pattern and field of view is for the sensor that we're operating, and then lastly, the AGL and speed of the airborne vehicle. The reason I bring all this up is it is very possible, if you don't understand the limitations of your sensor, to outfly its capabilities. And what you'll end up with is, if you're familiar with the Regal systems, the Minivux 1, 2, or 3, they're all line-based scanners. So if you're flying faster than a certain speed, those scan lines on the ground start spreading further and further apart. And you can certainly classify that data to ground. What you're going to end up with, though, is large smears between those lines because there's no information in that area. And then swath overlap. I bring this up just because there's some companies selling the equipment that will give you very unrealistic project design and running very low swath overlap line to line. It's very important for several different reasons. First, it's going to increase your point density. It's going to reduce laser shadowing by hitting targets from multiple different angles. It's also going to reduce the risk of gaps in the data due to turbulence. And that is especially critical when you're flying on an unmanned fixed wing system, because one flight line, the aircraft may have been completely level, no roll left to right from wind. On the next flight line, it may have been rolling back and forth. And so when we actually get into processing the data, we apply what's called an angle gate. And I'm kind of jumping ahead to the last point here. The data at the extreme edge of that swath tends to be noisy and less accurate. So when we're applying that angle gate, if we had a 90-degree field of view starting out, we're going to clip it down to 70, 35 degrees each side of nadir. So if you've got one flight line that was like nice and level, the other one the aircraft was rolling, it's very likely you'll end up with a void between those two flight lines if you don't have the proper overlap. And then treatment of project boundary, I'm not going to spend too long on this. Basically, the best practice that we would recommend is apply a 50 to 200 foot buffer. This gives us the opportunity to collect well outside the area that we're actually trying to map, so that we don't have voids or gaps around the edges of the project boundary itself. Control layout and distribution. One size does not fit all for control for these types of projects. The number of control points and the placement of them is going to vary based on the size and geometry of the project that you're working on. The general guidelines, we try to use hard, flat surfaces. We want to stay away from, inclined areas or vertical busts caused by curbing, anything like that. We want a nice uniform coverage throughout that AOI. And then we want all of our checkpoints to be spaced away from our control points. If we have them clustered up against the control, when we go to check the data against those validation points, it's going to start checking really well because it's right up against the control there. We look for photo identifiable features whenever we can. That might be pavement marking or turn arrows, stop bars, that type of stuff. And then we always try to take a picture in each cardinal direction and one up close of where that GPS rod tip is touching the ground. These are two examples of control layouts. The reason I picked these two, the one on the left is a greenfield solar development project. It's about an 80-acre site, but what you'll notice is it's completely wooded. So our ability to set control within the site is fairly limited because there's trees and stuff growing inside of there. The opening that is running through the site is a railroad track, and we're not allowed to go on that easement, and we don't want our crews to be working on that easement if a train comes by or something. And then the project on the right is a residential development project. So that one, it's a graded site. It's pretty wide open. We have got good access to go and set and panel control points where we want to. And then looking at wide area flight planning, to me personally, when I'm looking at a UAS project, anything over probably 300 or 400 acres, I would call wide area mapping. These are just two examples of flight plans. Project on the left is a solar project that we proposed down in Florida. You'll see we've got that crossing flight line that goes across the entire block that's used for the calibration and strip adjustment of the data back in the office. And then the other project on the right here, same one that I showed on the last slide, just showing the flight plans on it. Typically what we'll do when we're flight planning is we will take these flight lines and then overlay them on the control to verify that we're going to cover all of our control points. We're not going to have, cut too short and missed a control point that we need for calibration. And then corridor flight planning comes with its own set of considerations, particularly when you're mapping transmission lines, because that wire is always blowing and swaying in the wind there. So you don't want to have multiple passes going over the wire, or you're going to end up with, when you try to go into like a TopoDot software and vectorize the wire and classify it, you end up with conflicting wire positions that the technicians have to then try to sort through which one to follow. So what we'll do for transmission line mapping, if we're using a UAS on that, we'll have the center line, and then we'll create a buffer with either a 15 or 20 meter offset on either side of that center line. And that buffered edge is where we'll plan our flight lines so that we can follow the transmission easement. And we're getting one pass down and one pass back. And that's enough for us to model it without conflicting wire positions. This is the thing I meant to add about the corridor flight planning. So when you're planning for corridor flights, you've got to be concerned about lateral overlap from lift to lift. So one flight to the next, they have to overlap each other. So you've got to have enough turn data there to cut out and have no voids or gaps between those. And the same thing when you're dealing with the turn in a corridor. You've got to fly past that, come back around, and then get back on the next flight line, which is that, I'm red-green colorblind, so forgive me, but it's the green strip in the center there. That's that turn off the flight line, come back, get on that, get off that, and then get onto the blue line that's going to the east over there. Aerial targeting, that really needs to be appropriately sized according to the acquisition type and sensor characteristics. Some sensors are very sensitive to the size of the panel target that's used, which is why you see that large 4x4 iron cross panel target on the far left. The other thing that we're trying to consider when we're setting our aerial targeting and the control, especially in an urban area, is keeping the target away from overhead tree limbs, power wires, anything that's going to obscure it and cause us to get a bust against that control point when we go to calibrate the LiDAR against it. In this instance, what we did over here is we actually picked between two driveways where there was a fire hydrant, and we put the control point there so that we don't have a car that's going to come and park over the control point in the middle of our flight. And then aerial targeting on soft surfaces. Basically the key takeaway with this is when you set panels on soft surfaces, that center of your panel needs to be flat and flush with your either rod and cap or hub and tack that's set in the ground. What I've seen sometimes in the past is they have someone will have a hub in the ground and the panel's floating, 5 centimeters above it at this control point and 3 at the next and 1 at the next one. All you're doing if you have that is you're just introducing random error into your data set at that point. And then lastly, from a acquisition standpoint, for planning, base station setup and considerations, the main choice you have with this is, do you want to use a core station or do you want to use a local base station? Core stations are great if they're nearby to your project, but the reality is that sometimes they are not nearby enough, or they may be down for maintenance and you may not be aware of that. So we typically will almost always exclusively use a local base station set up and running on site. We want to keep that away from sources of signal shading and multipathing. Signal shading would be next to a building or next to trees. Multipathing would be keeping cars away from it, chain link fences, power wires. We want that stuff. We want the base station basically set in a very nice open field with good visibility to the sky. And then jumping into the processing, so every sensor is going to have its own proprietary processing software that the manufacturer will provide you with. So I didn't want to go into that because it's all kind of the same thing, but there's varying steps to it. So where I thought I'd pick up with is once we've got the raw aircraft trajectory and the raw laser data, the raw aircraft trajectory gets post-processed, merged with the laser data, now we've got a point cloud, simply put. So the next step from there is for us to actually go in and cut flight lines and remove all the turn data from one line to the next. The reason we need to do this is once we get that point cloud pulled into like a Terrascan environment, we need to be able to look at the relative accuracy of that point cloud. So how well does one flight line fit the next flight line? Is there vertical offsetting or horizontal offsetting from line to line? Cutting the flight lines allows us to then be able to go in and strip adjust all the data and match that either lift to lift or, line to line or block to block from separate lifts. And then moving ahead to the LiDAR processing side of things. So once we've got the data strip adjusted, we'll usually run a DZ raster at various intervals to verify that the strip adjustment process gave us a good result from it. And then we'll move on to actually classifying the LiDAR. So we use macros to do this for the most part. The best macro is going to get you maybe 90 to 95% of the way there. There's still 5 to 10% of that's going to be technicians going in and manually editing the ground class. And so that's what you're kind of seeing here. This is a countywide mapping project. It's one tile of LiDAR from probably 1,000 tiles in that project. So what we're looking for when we're manually editing is smears in the surface, pits, spikes, anything that looks unnatural against that surface. And so on the top left, you've got the ground class shown in orange, and then the buildings that are classified shown in purple. And on the top right is the shaded surface. And what I've circled there, and the arrow's pointing to it, is something that when I'm looking through that tile and I'm panning through, that caught my eye. It doesn't look natural against the surface. So what I do is I cut a cross section on it. And when I'm looking at it, sure enough, it's a building that's built up against the hillside. And the macro and Terrascan saw that planar roof and classified it as ground. So what I've got to do is go in there and manually edit it, remove it, and put it in the building class. And the same type of thing goes for bridge decks. Bridge decks by convention are not left in the ground class. So in this example, I've already taken, you can kind of see the green in terms of the intensity there. I've already moved that bridge deck from ground to the bridge deck class. And then on the shaded surface on the bottom right, you can kind of see the idea of the smears I was talking about. So the next step for us would actually be to go in there and put brake lines at the top of the abutment and at the bottom of that slope as well to enforce that terrain model. And then last thing here, this is just a quick overview of a project that we flew. So this would be an idea of taking all the stuff we've talked about and using that to support something maybe outside the realm of a normal GIS project, more geared towards a topographic survey for our survey group. But in this case, we're collecting LiDAR and digital imagery, using that to support the field survey of a monofill site. Monofill is basically a landfill where they're landfilling one type of material. In this case, it's a coal ash. Some of those different deliverables. The one that I want to call out is the FGDC compliant metadata. For those of you who are in the point counterpoint thing in lunch today, Megan was talking about the importance of FGDC compliant metadata. So for all of our projects, that's something that I'm personally sitting down and writing for each project. This will give you a good idea of the full point cloud. So that's actually classified for ground and low, medium, and high vegetation. So it's running in MicroStation through TerraScan, but you can see the DTM, all of our break lines are digitized in, and it's visualized by elevation and intensity of the return. And in a second here, it'll just go to strictly the ground class by itself. And so that's what the ground class alone will look like. And this is what we'll use to go in and actually start digitizing break lines where we need them, and then picking up any other features that we need to. This is a look at the digital terrain model from the same project. The DTM, the main difference between that and the DEM is you're just encompassing all your break lines in that model. The other difference too is it's really hard to see here because it's against the background is dark and the points are red, but if you can see it, there's hundreds of red points still on that surface. And what those are, we take the class 2 ground and we thin that down into what's called model key points. The way that works is if you think of the flat plane of a table, the software is looking at the LiDAR data, and if it sees a flat plane, it'll use a point on each corner and one in the center to model that flat plane. But when it runs into areas of terrain change, it'll start pulling in more and more of that ground classified LiDAR to maintain the representation of the terrain in that area. And then this is a look at the tin surface and the contours. The tin surface, each of the vertices of those triangles is from the model key points that we generate. The model key points are also what allows us to bring that LiDAR data into a Civil 3D environment and load it in there without Civil 3D choking up and crashing. And then the contours, the 1 foot contours, we actually derive those off the tin surface itself. And so that's everything I got for you guys. Any questions? Go ahead.
When you have to go in and manually change your data, like for example, when you're talking about the building that was close to the hill, is that going to remain as spatially accurate as the points that were collected from the LiDAR, or are you willing to like give up a little of that to make the data accurate to what it actually is?
It's a good question. So the question was, when we go in and manually edit, for example, the building that I showed you on that one slide, does it maintain the spatial accuracy or does that change? I think so the answer to that is you're not actually changing the spatial accuracy of the points. All you're doing is taking them and reclassifying them and saying, okay, TerraScan thought this was ground. No, it's actually a building. Just cut a cross section, classify above line, and move them all to the building class or the ground. Yeah, building class in this case.
So the location is accurate, just they've classified it.
Yes. Okay. So we're not modifying the location. We're just modifying what the software thought it was. So, go ahead.
Are there any other sensors that you can integrate with the point cloud, like near infrared or anything like that, or is it kind of two separate data sets?
The question was, are there any other sensors we can integrate with this type of data, such as near infrared? That's a good question. There was a veg encroachment study that I did when I was at a previous firm where that was going to be part of the project. We were going to collect LiDAR, 3-band RGB, and then multispectral imagery as well, to be able to overlay the multispectral with the LiDAR to identify what tree is actually a dead standing tree that could fall into the line. That was not part of the project that ended up getting picked up, but I'm sure it's possible. It's just not something I've done myself.
Okay, thanks.
Sure. Go ahead.
When you work with terrain
The question was, have I done any work with green laser or topobathy lidar? I have not. We do have. It doesn't operate really on the same principle because it's using sonar, but we've got side scan sonar and multi-beam sonar for hydrospatial type projects. But I haven't personally done anything with topobathy lidar in my career. I want to. That's the next place I'm trying to go. Yeah.
Do you use like autonomous modes for the sonar, or is it manual?
No, I don't. That hydro group is, they're part of the geospatial services group. I don't think they've got a hydro boat that they use. We did look at a project for them for a coal ash pond where they couldn't get their boat into the pond. And I think we were going to try to test a UAS topobathy system, but we never got around to it on that one. I think we ended up flying that manned. And I don't know that that was a manned topobathy flight though. So, sure.
So, you brought that up, the RGB band plus elevation points. I don't see much of that. Are there just not companies flying them, or is it just prohibitively expensive?
So the question was, and if I'm summarizing correctly, LiDAR mixed with the 3-band imagery as far as like colorizing the point cloud. Yeah, there's software that will do it for you. The reality is we used to colorize. When I worked at my previous firm, we used to colorize everything because the imagery was already there, it was co-collected. We could colorize it right away and use it. And it does help when you're trying to classify certain features. I mean, I remember working on a transmission line where I couldn't tell what was going on, but it was like a fire pit built right below the transmission line in the corridor. And when I moved from intensity to 3-band RGB for the colorized LiDAR, I could see right away, okay, someone built a fire pit where there wasn't supposed to be one. It gets done. It's just not something that we very commonly do unless a client requests specifically wanting colorized LiDAR.